You know that feeling when you ask an AI for something simple and it comes back with a totally bizarre answer? Yeah, you're not alone. Today, we're going to pull back the curtain on AI and look at one of its absolute biggest challenges. How do you teach a machine what we mean and not just what we literally say?
So here's the game plan. We'll start with why this is such a tough problem in the first place, then we'll check out the special language created to deal with it. We'll see how AI tries to decode our conversations, how it handles the real messy world, and finally, we'll talk about the fundamental quest at the heart of this entire field. All right, let's dive right in with Section 1, the challenge of context. This is all about why these incredibly powerful AIs can get things so wrong.
I mean, we've all been there, right? You've got this tool that can write code or create amazing art, but then sometimes it just completely fumbles a simple request. It doesn't get the joke or it misses the point entirely. So, what is going on there?
Well, it turns out it's not just some random glitch or a simple programming error. It's actually a huge, well-known problem that computer scientists call the challenge of context. It's a fundamental hurdle.
And this is no small thing. Researchers actually see this as a central part of AI's quest to represent knowledge. I mean, think about that phrase. The whole goal is to figure out how a machine can actually understand meaning, not just spit back data it's seen before. It's one of the biggest mountains they have to climb.
So, that brings us to our next part. How do you even start to solve a problem that big? Well, first, researchers had to invent a way to even talk about context in a formal way. They had to give the AI the rules of the game.
Okay, now this might look a little technical, but stick with me because the idea is actually brilliantly simple. Researchers came up with this notation, IST-CP. It's just a clean mathematical way of saying, in context C, the proposition P is true. That's it. And here's where it clicks. Let's take the word bill. If our context, our C, is at the bank, then the statement bill means money is true. But if we switch the context to in Congress, the meaning completely changes. Now, the statement bill means legislation is true. This simple little tool is the first step in teaching an AI how to tell the difference.
And this isn't just a one-off trick. The endgame here is to build an entire formal language around this idea. The goal is to create a rock-solid system that lets an AI reliably and consistently reason about thousands of different contexts without getting all mixed up. Okay, so that formal logic is great, but what happens when you apply it to messy, everyday human conversation? Well, that brings us to Section 3, decoding human language. We're moving from just a string of words to what they actually mean.
To handle the way we talk, researchers developed something called Discourse Representation Theory, or DRT. You can think of it as a special toolkit for an AI. It helps the AI read sentences one after the other, building up a single picture of what's being said, and crucially, keeping track of how words connect to each other.
Here's a perfect example of how that works. An AI reads the first sentence. A developer wrote code. Got it. Then it reads the next one. It had a bug. Now for us, it's obvious that it refers to the code, but an AI needs rules for that. DRT provides the formal logic to correctly link it back to code and not to the developer. This is absolutely essential for understanding basically anything longer than a single sentence. But the real world is so much more than just a series of clean sentences, right? It's messy, it's uncertain, it's always changing. And that leads us to our fourth section, how AI tries to operate in this dynamic world. So traditional logic is very black and white. Something is either true or it's false. It's an on-off light switch. But think about words like warm or tall. They're not absolutes. This is where something called fuzzy logic comes in. It allows for degrees of truth. So instead of a hard on-off switch, it's more like a dimmer switch, which is way better for describing how we humans actually talk. The formal system for this is called Fuzzy Axiomatic Set Theory, or AFS. And what makes it so powerful is that it lets an AI handle two different kinds of uncertainty in one go. The subjective fuzziness of our language, like the word warm, and the objective randomness of the world, like the 50-50 chance of a coin landing on heads. So in a system like this, a statement isn't just true. It might be assigned a value, let's say 0.9. That number just means it's mostly true, but not with 100% certainty. This allows for a much more sophisticated and nuanced kind of reasoning that's closer to how our own brains work. And fuzzy logic is just one tool in the toolbox. To deal with the world that is constantly in motion, researchers have developed whole families of specialized logics. These are systems designed to help an AI reason about how its own knowledge changes, to understand time and the sequence of events, and to make sense of complex systems that never sit still. And all of these tools, all of this logic, it all brings us to our final section. It brings us to the never-ending quest and the fundamental tension that sits right at the very heart of artificial intelligence. See, it all boils down to this classic idea: syntax versus semantics. Syntax is just the symbols, the letters C-A-T. A machine can get incredibly good at manipulating syntax. But semantics, well, that's the meaning. That's the actual concept of a cat that pops into your head. The furriness, the purring, the whole thing. And that's it. That's the whole game right there. The entire struggle of AI and the purpose of all these formal systems we've looked at is to teach a machine how to cross that bridge, how to go from just processing the letters C-A-T to actually grasping the rich, complex meaning of what a cat is. Which leaves us with one final and pretty deep question. If a machine gets so good that it masters every single logical rule of context we can throw at it, if it can navigate any conversation and any ambiguity perfectly, does it truly understand? Or is it just the most sophisticated parrot the world has ever seen? That's the question that keeps this whole field pushing forward.